All right, ready for this. We're going deep on the Fibonacci sequence. You know that thing, 1, 1, 2, 3, 5. You add the last two numbers to get the next.
Classic.
But get this, it's not just some pattern, right? It actually links to this thing called the golden ratio, which is like hidden everywhere. Art, architecture, even nature itself.
It's true. It pops up in the most unexpected places.
And today, we're going beyond the basics.
Right.
Like, how does this Fibonacci thing play out in geometry? And get this, even the packing of spheres. I know, right? Wild.
Well, the golden ratio actually has a very specific definition in classical geometry.
Yeah.
Imagine you're dividing a line, but not just in half. You're dividing it so the ratio of the whole line to the bigger part is the same as the bigger part to the smaller part.
Whoa, okay, that's a lot of parts.
Yeah, it sounds complicated, but think of it like a rectangle.
Yeah.
If the sides of the rectangle are in this special ratio, about 1.618, boom, you've got the golden ratio.
Okay, so it's like a rectangle with a certain, proportion?
Exactly.
Yeah.
And that proportion, it shows up everywhere. You mentioned architecture earlier. Think of those ancient Greek temples.
Oh, right.
Or even something as common as like a credit card. The ratio of the sides is often really close to the golden ratio.
Never thought of that.
And then there's the arrangement of petals and some flowers.
They're all golden ratioed out.
It's like this hidden harmony in the way things are structured.
So we're talking like a secret code, but it's just shapes.
Kind of. And that's what makes this whole thing so fascinating. We're about to see how this, honestly, pretty simple ratio pops up in some really unexpected places.
And that's where, if I'm remembering right, figure 16.01 comes in. It's like visual proof of the Fibonacci golden ratio connection, yeah.
Exactly. If you look at it, you can see how quickly the ratio between those Fibonacci numbers, one after the other in the sequence, they get closer and closer to that 1.618, the golden ratio.
And it happens fast.
Yeah, it's not just about having like huge EE numbers in the sequence. The pattern shows up almost right away. It's like,
It's programmed in. Like, it can't help it.
right. And then there's figure 16.02, which shows if you take ratios of Fibonacci numbers that are further apart, like not just right next to each other.
Oh, things get even wilder.
You get numbers that are really close to powers of the golden ratio. And this is where it gets really cool, because it shows us that there's even more to the Fibonacci sequence than we thought.
Deeper, you mean?
It's not just about adding numbers. There's this underlying mathematical connection to the golden ratio itself.
Okay, so get ready for this, because now we're going to talk about spheres.
Here we go.
So our sources mention this thing called close packing of spheres, or CPS. It's like, how do you pack spheres together in the tightest way possible? Like, imagine you're stacking oranges at the grocery store.
Exactly. You want to fit as many as you can in the smallest space.
Right. So it turns out this whole sphere packing thing links back to the golden ratio and Fibonacci sequence.
It's true. And it's actually pretty amazing how it all comes together. When you pack spheres this way, you start to see these patterns emerge. And those patterns, they form a shape called an icosahedron.
An icosa what now?
An icosahedron. It's a shape with 20 sides, and you can actually build one using just 3 golden rectangles.
Whoa, really?
Yeah, if you're looking at the figures, it's figure 16.03. It shows it way better than I can explain it.
Okay, I see it. Those rectangles kind of like intersecting inside that shape. But how does Fibonacci fit into all of this?
So if you look closer at the rectangles, those are in figure 16.04. The ratio of their sides is 26 to 16,
Okay.
which is like 1.625. Really close to the golden ratio, right?
Oh, wow. It's like those golden rectangles are hidden inside the icosahedron.
Exactly. And it gets even cooler. Remember how we talked about the Fibonacci sequence? You add the last 2 numbers to get the next one? Well, those side lengths we just talked about,
Right.
15 and 26.
Yeah.
You can actually use those to start a whole new Fibonacci sequence.
Wait, what? Really?
Yeah. 16, 26, 42, 68. It goes on and on.
So it's Fibonacci inside of Fibonacci. I love it. Okay, so we've got the golden ratio in the Fibonacci sequence itself. And now we're seeing it in the shapes that we get when we pack spheres as efficiently as possible.
It's like this hidden code that connects everything.
Right. It's everywhere.
And it makes you realize that the golden ratio, it's not just some random abstract math thing, it's like woven into the very fabric of how things fit together in space.
It's like we're peeking behind the curtain of the universe.
Exactly.
And speaking of the universe and its love for these patterns, can we talk about figure 16.05? That image of the great stelled dodecahedron just blows my mind.
It's an amazing image, right?
It's like, woo.
And it shows us how all of these concepts are connected. If you look at it, you can see these nested pentagons inside the shape. And they all relate back to the golden ratio.
It's like a mathematical nesting doll, patterns within patterns, and they all come back to this one simple ratio.
Exactly. And the thing is, we've really only just scratched the surface here.
There's more.
Oh, yeah. Like, think about this, the Fibonacci sequence and the golden ratio. They're not just about addition, they're also related to multiplication.
Whoa, okay, things are about to get even more interesting. I can feel it.
And that's where this thing called the arithmetic geometric mean comes in.
Okay, so you were saying something about the Fibonacci sequence, the golden ratio, and multiplication, this arithmetic geometric mean thing.
Yeah. It's like we've been talking about adding the numbers in the Fibonacci sequence, right?
Mm-hmm.
But then there's this whole other layer with multiplication, and that's where the arithmetic geometric mean, AGM for short, comes in.
AGM, got it. Okay, so before we get like totally lost in the math weeds here, can you break that down? What's so special about this AGM thing?
Okay, so imagine you've got two numbers, any two numbers. The AGM is a way to find, like, this balance point between them. It gives you a number that represents both their average, like adding them together and dividing by 2, and also kind of geometric average, which involves multiplication.
Okay, I'm kind of following, but how does this tie back to the golden ratio and Fibonacci?
Here's the amazing part. The golden ratio sequence itself, those numbers we've been talking about, they actually embody this balance.
Get out.
Yeah. Each number in the sequence is not only the sum of the two numbers before it, but it's also this perfect balance point between addition and multiplication, that AGM thing we're talking about. It's like built right in.
So it's like this hidden harmony between like totally different math operations, and the golden ratio is right there in the middle of it all. I love it.
Right. And it gets even wilder because the great mathematician Gauss, he once said that the complex domain, that's the world of numbers where you have imaginary numbers, all that, he called it the domain of the arithmetic geometric mean.
Well, hold on. So you're saying that this connection we're talking about, this AGM thing, it goes even deeper than we thought.
It makes you wonder,
Yeah.
right? Like, what else is connected to this?
It's like we started out exploring these patterns in geometry, in nature, with seashells and stuff, and now we're seeing that they're also embedded in the very foundation of math itself.
Exactly. And honestly, we've only just scratched the surface. Think about it. What other connections are out there just waiting to be discovered, hidden in plain sight?
It's like the universe is speaking to us in this, like, secret code.
Maybe it is. And the more we learn, the more we realize just how much we don't know yet.
That's the beauty of it, right? There's always more to explore. Well, this has been an incredible deep dive. I feel like my brain just went through a blender in the best way possible. We started with the Fibonacci sequence, the simple pattern of adding numbers, and ended up talking about the geometry of spheres, the hidden structure of math. It's mind-blowing.
It really makes you appreciate the elegance of math and how it connects to literally everything.
It's everywhere. So to everyone listening, keep your eyes open for those unexpected patterns, those hidden connections. You never know where you might find the golden ratio popping up next. Thanks for joining us on this amazing journey.